Hi everybody and welcome to a new video in the Deep Learning Audio Application from Design to Deployment series. This time we're going to prepare a dataset that then we're going to feed to our keyword spotting system. So first of all, we should look into the dataset that we're going to use. And so for our simple speech recognition system, I've chosen this dataset that was released by Google a couple of years, 2 or 3 years ago, and it's called the Speech Commands dataset. So this is kind of a really interesting dataset because you have 65,000 audio files, and you have 30 different short words in there, and each audio file lasts for 1 second. So if you want to download this so that you can follow along with my tutorials, so you can come like to this link. Don't worry about the link specifically because I'm going to post it in the description section. And then you can come over here and download the dataset. Okay, so I'll show you how the dataset looks like. Okay, so I've imported it here in my projects folder. So we get in here. So originally you have 30 different folders, and for each folder you have a specific keyword or word. But I've just taken a subset of the 30 words, and I'm using like this 10 words that are probably the most common that you would use in a vocal user interface. So like down, go, left, no, off, on, right, stop, up, and yes. And if we go inside like this folders, so for example here in down, so you'll see that you have a list of all the audio examples. So let's listen to one.
Down.
Down, that's great. Good. Okay, so now let's go back to PyCharm. The main question is, how are we going to prepare our dataset? Well, the basic idea here is that we're going to extract an audio feature for each of the audio samples that we have in our dataset, and then we're going to store that in a JSON file. Now, you may be wondering, what audio feature are we going to extract? Well, I'm going to respond to that question super quickly. It's the MFCC, which stands for Mel Frequency Cepstral Coefficients. So this is an audio feature that's commonly used for audio classification. So you would use this for speech recognition, and it's not a case that we are using this, but also for music instrument classification or for detecting different music genres. And the reason why we use MFCCs is because these coefficients tell us a lot about the timbre of an audio signal. Right, so now I'm not going to give you too much details about MFCCs because I've covered this quite in detail in another video that you should find over here, and I have a whole series that's called Deep Learning for Audio with Python if you want to dig in more about these audio features and audio related like topics. So I'm just going to cover like the basic things that you need to know to follow along. So what an MFCC does, so when we extract an MFCC, what we do basically is we take snapshots at different segments of an audio file. So, and these snapshots basically are the MFCC coefficients. And so we can decide to take a variable number, different numbers of MFCCs. And so what we are going to do basically is going to be using 13 coefficients. And so the type of data that we're going to extract is two-dimensional. So we're going to have an array where like the first dimension is going to be equal to the time steps, to the number of time steps or number of segments. At each segment, we are going to take 13 coefficients. So it's as if like we were getting like snapshots at each time segment. And these snapshots are given by these MFCCs. And so this 13 is basically the number of coefficients. Right. So how do we extract MFCCs from audio signal? Well, we're not going to build an MFCC extractor from scratch. Rather, we're going to import a super handy audio processing library in Python that's called Librosa. Again, I've covered how to use Librosa in my Deep Learning for Audio with Python series. So there's a video where I go into the detail with that. So you should check that out if you want to learn more about that. But moving on. So we're going to need Librosa, and then we're going to need another couple of modules. So the first one being OS, because we're going to manipulate files. And then we're also going to import JSON, because we're going to create JSON files. Okay, so here I want to specify a few constants. And these constants are going to be handy when we pass in information to our prepare dataset function. Okay, so the first constant is just the dataset path. And this is equal to dataset. So basically, I'm setting the relative path to dataset, which is this folder over here. Good. The second constant is going to be JSON path. And so here I want to specify the path where we want to store this data that we'll use for training. Okay, so here we'll call this data.json. So we'll save this in the current folder. Okay, and moving on, we want to specify another constant, which is the samples to consider. Okay, so an audio file basically has a number of samples, and here we want to decide how many samples we want to consider for processing data. And so we'll set this to 22,050. So you may be wondering, but why are we using this? Well, it turns out that this is 1 second worth of sound given the default settings that Librosa uses for loading audio files. So let me explain that. So when we load an audio file with Librosa loads it using this sample rate. And the sample rate is the number of samples in a second. So we have 22,050 samples in a second when we load with Librosa. And this is the amount of samples that we want to consider, because we know that the audio files in the dataset that we have have a duration of 1 second, which is equal to 22,050, given we have this sample rate. Okay, so I hope this was clear, but now we'll move on to the main function that we'll use for pre-processing this dataset. So we'll call it, not surprisingly, prepare dataset. Okay, and so here we're going to have a bunch of arguments. But what prepare dataset is going to do is basically it's going to go through all the audio files, extract the MFCCs, store in a JSON file, all of that information. And that data is going to then be used by our deep learning model for training purposes. And so you may be wondering, but why aren't we doing this just like in real time? Well, it turns out that it takes quite a lot of time to pre-process all of this data. So it's better just to do that offline, then save all of that information in a JSON file and then retrieve it at training time. Cool. So as I said, we have a bunch of arguments for a prepared dataset. So the first one is dataset path. It's quite self-explanatory, isn't it? So we pass the path that we want to read for our dataset. Then we pass the JSON path, so where we want to save our JSON file with the data. And then we're going to pass 3 arguments that are specific to the MFCC extractor. So I'm going to try to give you an idea of what these arguments are, but again, I'm not going to get into the details because that is a huge topic in itself. Cool. Okay, so the first is first argument is quite self-explanatory, and this is the number of coefficients that we want to extract, and we'll put this to 13. So we're going to extract 13 coefficients, and then we'll pass in another value that's called the hop length, and the hop length is measured in number of frames, and we'll pass this to hop length 512, which is a quite customary hop length for extracting like MFCCs. So now you may be wondering, but what's the hop length? If you remember, guys, I said that when we extract MFCCs, we divide the audio signal into equal segments with equal length, and then we take a snapshot with MFCCs at each of these segments. The hop length tells us how big like the segment should be in number of frames. Good. And finally, we have another argument that I'll pass in. That's the number relative to the fast Fourier transform. And well, this is a lot to take in and understand that, but you don't need to know the details here. And again, if you want to know that, I have a video that explains like all of that. But basically, when we perform MFCC extraction under the hood, we do a fast Fourier transform. And then here, NFFT basically tells us like how big the window for the fast Fourier transform we want to consider. And we'll set this to a customary 2048. Good. So now we should start writing this prepare dataset function. So the first thing that I want to do here is to create a data dictionary. And here we're going to store all the data that we extract from the audio files. So I'll call this dictionary data. And then I want to store a bunch of different things here. So the first thing is the mappings. And this is going to be equal to a list. So with the mappings, basically what we want to do is map the different keywords. So for example, on, off, and so on and so forth, to different numbers. And so on is going to be mapped to 0, which is the 0 index of this list, and off is going to be mapped to 1, right? So why do we do that? Well, we do that because we can't pass words to our neural network. Rather, we should pass numbers. And so we want to map these keywords to numbers because of that. Good. So we're going to create these mappings. Then we want to create the labels. So the labels are going to be themselves a list. And here we're going to have values like these, for example. And so we're going to have one value for each of the audio files we have in the dataset. And so this value is basically like the target value that we are expecting. So here we are basically saying that the 0 index data that we are passing into the neural network for training is equal to on, right? Whereas this value over here says that the 0, 1, 2, the second index data that we're passing, audio file that we're passing to the deep learning model is equal to 1, which we know for the mappings is basically off. So these are like the outputs that we expect, the target outputs that we expect. Now, obviously, we also need the inputs for training. And we are going to, oh, sorry, not data, but we're going to call this MFCCs. Well, this is quite self-explanatory, right? And so here we're basically going to input the MFCCs for each of the audio files that we have. So the MFCCs are going to be the inputs, and the labels here are going to be the expected outputs. Great. And finally, we want also the files. So we want the file names with the path for each of the audio files. So for example, we could have something like this. So say for example, dataset on one.wav, right? And so basically here we are saying that the first audio file that we've analyzed, processed is at this path over here. So why do we do that? Well, we do that because we may want to go back to the audio files, like, and do some kind of like analysis on the audio files. And if we just have like labels and MFCCs, we're not going to be able like to go there. And we may want to do some kind of like manual analysis to understand why like certain like categories or labels are picked up and why certain others are not. So we want to have this kind of reference here. Good. Now, obviously, if I leave this Python and the Python interpreter is going to throw an error, so I need to remove all of this, and we're going to build this data programmatically. Right. Okay. So now the first thing that we want to do here is loop through all the subdirs, right? Okay. So what this basically means is that if we open up like this data set over here, we want to loop through all of these guys here. Okay. So how do we do that? Well, here we have some magic coming from Python that's going to help us do that. Okay, so let me write this. So we'll do for I, and here we have a tuple, and here we'll have a dir path, dir names, and file names over here, and we'll do in enumerate, and then we'll use os.walk, and then we'll pass in the dataset path. Okay, so what's this madness here? Well, it's kind of like quite simple. So basically, so what walk enables us to do is to walk through a folder structure recursively, and in this case from the top down towards like the top down, right? So from the top towards the bottom. And so basically here at each iteration we're going to get like the path of a directory, and then all the name of the subdirectories in that directory, and then the file names that are in the dir path. Right? And so basically what's going to happen is that we're going to start here with this data set, which is our root, and then we're going to recursively go into down, and then we're going to move to go, left, no, off, so on and so forth. Now we need to ensure that we are not at the dataset level. So in other words, we need to ensure that we are not at a root level. So to do that, we'll use a conditional statement here. So we'll say if dir path is not dataset path, and then we'll do some magic over here. Well, so why should I specify this? Well, because os.walk starts from the dataset path in this case, and then it recursively goes down to the subdirs. But we're not interested in dataset path itself, so we want to skip that. Now we need to specify what kind of magic we want to do here. Okay, so we want to, as a first thing, update the mappings. Okay, so let's do that. Well, first of all, let's scroll a little bit, and now let's update the mappings here. So we'll do a data mappings, and we'll append. And what should we append? Well, we should append the category name, just category. But we need to extract this category first. And so how do we do that? Well, this is quite simple. So we have this dir path, and so we can take the dir path, and then we do dot split, and we're gonna split using the slash. And what this basically means is that so the dir path in this case could be something like dataset say down, and then when we split using this slash sign as a divider, we're going to get a list like this. And so in the list, we're going to have dataset, and we're going to have down. And now the name of the category is this guy here, down, which is the last index. And so we need to get that. And so we'll add this down here, and now we should have the category name. Great. And so we can append that to mappings over here, and then we're all set. Good. So the next thing that we want to do is going through all the file names. So loop through all the file names and extract MFCCs. Right. So we'll do that by doing for f in file names. And now we need to do a bunch of things. So first of all, so now here in this loop, we are like at the level of each audio file in each of the different like folders. And so here we'll do, as the first thing, we want to get the file path, because these file names just have the name of the file. So we need to extract the whole or reconstruct the whole path. Then we want to not lead, but load the audio file. So then once we've loaded the audio file, we want to ensure the audio file is is at least 1 second, right? Because we're going to ignore all the audio files that are shorter than that. Cool. Okay, so let's start by getting the file path. Okay, so here we'll do file path, and file path is equal to os.path.join. And we are going to join the it's the dir path with f. And so here we're joining like the dir path with the file name. And so this gives us the whole file path. Okay, so now we want to load the audio file. And so when we load, we with something with Librosa, we get both the signal itself as well as the sample rate. And so here we're going to do a Librosa dot load, and here we need to pass the path in, and this is the file path. Good. Okay, so now we want to ensure the audio file is at least 1 second long, and here we can use another conditional statement. So we can say if the length of signal is, where is it? Greater or equal to, I think it's called, samples to consider, then we do some stuff. Right. So you may be wondering, but why are we considering only the audio files which are like longer, at least like 1 second long? Well, because when you use a CNN, a convolutional neural network, you want for the input data to be of the same shape, having like the same dimensions. And so we need to ensure that we have audio files that have like the same shape. And indeed, not only we are interested in saying that in considering only like the files that are at least like 1 second long, but we want to ensure audio file, well, we should actually say enforce 1 second long. So enforce 1 second long signal. So here we may have like audio files that are longer at that 1 second. And so we want to take like this signal, and to ensure that we just take signals that are 1 second long, we'll take this and we'll just consider the first second worth of data that may be longer than that. Cool. Okay, so now we know that the signal that we are getting has like this number of like samples, which is equal to 22,050, which is basically 1 second worth of sound. Great. Now we should do a bunch of other things here, obviously. So we extract the MFCCs over here, and then we store data. So how do we extract MFCCs? Well, this is particularly simple with LibRosa, because LibRosa has a module called feature that has a function that's called MFCC that enables us to extract MFCCs super simply. Okay, so here we'll pass in the signal, and then we'll pass in basically these arguments over here. So we can just copy them. We'll take that, we'll put it in here. So here though, we'll call this number of MFCC. Then this is hop length, and this is n, or the window for the fast Fourier transform. So as you've noticed, I've basically used the same naming conventions that LibRosa uses. So this is like the optional argument, like from the MFCC method from LibRosa, and here I have, for example, our argument over here. Cool. Okay, so now we have the MFCCs, and now we need to store all the data. So what we want to store here is the labels, we want to store the MFCCs, and the file name. Okay, so let's start with the labels first. Okay, so here we'll do a data, and here we'll use like labels, and then we'll append, and here the label is going to be equal to I minus 1. Good. And so now you may be wondering about why is this, so first of all, what's this I, and what's this, why are we like subtracting 1 to I? Well, I, if you guys remember, is the count that we have in the most external loop that we have, which is the one that goes through all the subdirectories here. So as I mentioned, when we use OS walk, so the first iteration is going to be equal to the root level, which is dataset, and that's going to be equal to 0. Then down, for example, in this case, is going to be equal to 1, then go equal to 2. And so we want for down to be equal to 0. So we have to subtract 1 to the current iteration we're in, which in this case is probably going to be 1. So this is why we're doing I minus 1. Great. Okay, so this is the for the labels. Now we want to store the MFCCs, and so we're going to do that by appending MFCCs. But what we get out of LibRosa is a ND array. So it's a NumPy array. So First of all, I want just like to get like the transpose of that array that we have, and then I want to cast this to a list. And the reason why we're going to do that is because we can't store directly, like from an ND array, we can store that directly into a JSON file. So we have to cast that to like a Python list first. Good. Okay, then moving on, the last thing that we want to save is the file name. And so here we'll take data files.append, and here we'll pass in the, well, not the file name, but the file path. Good. Okay, so now we've basically have done most of the work for like this pre-process work. And so I want to just review this a second and add a couple of print statements here and there so that we'll see this like in action when we run the script. Okay, so here, just to wrap up, so we have the data dictionary that we'll use to for the mappings and for all the data with both like the inputs and the outputs. So here in this first for loop, we go through all the subdirectories, so through all the categories. Then we ensure that we're not at root level, and then at this point we just like add like the category to the mappings, and then we go through all the files, all the audio files in a category, and then here we just like load the audio file. Then we ensure that we have an audio file that's a signal that has the samples to consider number of samples, which is equal to 1 second. Then we extract the MFCCs, and then we store all of that information in. Okay, so as I said, I want to add a couple of print statements, because otherwise when we run this, we're not going to be able to see anything. So I'm going to use an F string here, and I'll say processing. So here I want to just pass in the category. So here basically we're gonna see like a statement which says processing, I don't know, like down, or processing go. And then when we process all the file names in a category, then we want to see that we're making some progress. And so I'm gonna have another print statement here with another F string, and here I want to pass in the audio file, the file path, and this is going to be equal to file path, and then the label, which we saw is equal to I minus 1. Good. Okay, so now at the end of these for loops, we are going to have our data dictionary. So the last thing that remains to do is to store in a JSON file. Okay, so let me see. Yes. Okay, and so we'll do that using with open, and we'll open a new file. We'll write a new file which is going to be at JSON path, and then we'll open this in a write mode because we want to write stuff, and then we'll do as FP, and then over here we are going to do a JSON dot dump, and here, oops, here we go. So here we need to pass the data in, and so this is the data that we want to pass in. Then we'll pass the file, and then we'll use an optional argument here, and I'll set the indent equal to 4 so that we're going to have a nice layout for our JSON file. Good. So this is it. So this is the whole pre-processing function that we're going to use. And so now, in order to use it, we need to write like a very simple very simple instructions over here. So if we run this like as main, if we run the script as main, then we want to run prepare dataset, and here we'll pass in dataset path, we'll pass in JSON path, and then we'll just use this default values over here, so we don't need to do anything else other than this. Cool. So if I don't have any mistakes in this code, so we should be able to run this smoothly and get like a JSON file with all the data. Okay, so I'm gonna run this now. So let's see if this works. Yes, it seems to be working. Great, but it's gonna take some time to process like all the data. So I'm gonna just like stop the video here and resume once it's finished. And here we are back. So the process finished, and so now I have a nice data.json file in here, and so we can analyze that. And so as you can see here, we have our mappings. And so here we have like all the different categories that are mapped to like the different indexes in this list. And we have our labels. And then somewhere down here, we're going to have like our MFCCs. And then finally down here, we're going to have all of our file names that we've processed. Good. Okay. So we're basically done with this preparing dataset task. And so now you're able like to prepare like all the data like for our keyword spotting system. So I hope you've enjoyed this video, and if that's the case, yeah, just like remember to like the video and subscribe and hit the notification bell like to get more videos in the series and more stuff like this. So next time we're gonna basically build our keyword spotting system using TensorFlow, and we're gonna train it. So stay tuned, and until the next time, bye.